Hello everyone, my name is Mandalari and I'm a research associate at Imperial College, London. I'm now presenting a joint work with Northeastern University which focuses on identifying and mitigating non-essential IoT traffic. We know that any object nowadays can be connected to the internet. From smart speakers to cameras, even your fridge can be connected to the internet. And we call this Internet of Things devices. And they are great. We can ask them to shop for us, they play music for us. While these devices often come with convenient services, they open the door to numerous privacy and security risks. These devices often expose information to a large number of destinations, including third parties, advertising, and tracking services. One of the critical steps that will enable transparency and privacy by default is solution at edge, at consumer zone. We need an automated framework for detecting and isolating non-critical communication from IoT devices that automatically blocks any connection that are non-essential for the functionality. For this approach to work, we need a systematic approach to identify and block traffic that is non-essential for a device to work, with a little to no user configuration. Since the IoT devices can potentially expose information about its users to any destination, since most IoT traffic is encrypted or encoded, and the vast majority of IoT systems are closed, it is infeasible to perfectly infer what information is exposed through network connection using black box techniques. So, from our previous work, we learned that some traffic is essential and some is not essential, so we had an idea. Maybe we can block some non-essential communication and still be able to use the device. We have three main goals here. The first one is to develop a methodology for automatically identifying non-essential IoT traffic, and in this case we seek to understand which destinations are not required for the device functionality so that we can block them to mitigate their potential risk. And to address this, we propose a methodology for automatically detecting whether a network traffic destination is required or not for a given functionality. Second, we want to understand what is the nature of the non-essential IoT traffic, so armed with a measurements methodology to detect non-essential traffic. We apply it to identify and study non-essential traffic produced by our set of popular IoT devices. As part of this research question, we are interested in the type of destinations contacted. And finally, we want to understand how we can mitigate non-essential IoT traffic. So the knowledge of what destinations can be blocked for every device allows us to make automatic runtime decisions on what traffic to allow or not in a typical IoT deployment. As any other research idea that we had until now, there are various challenges that we need to be addressed, and the main challenge is automation. IoT devices are very hard to test automatically. They offer very different functionalities. They suffer, in our experience, from frequent blackout that must be detected, and they typically require user interaction, so they are not directly programmable. It's very hard to verify if a functionality was actually executed or not. But we had some ideas. We can use companion devices of phones and voice assistants, and we can use network traffic patterns to classify IoT devices' response. We consider IoT devices as a black box, so we have no control over how an IoT device works internally. We do not look at the content of IoT communication, which is mostly encrypted, so no content interception and inference. We do not test all the functions. We consider the most characterizing, one depending on the device category, and it must be initiated by the user. So we develop a measurement methodology and we consider 31 devices in total, and we have a router with IP filtering and DNS filtering capabilities. We have power plugs and scripts to power cycle the devices. We have trigger script to invoke IoT devices functionality. We have companion app interaction and voice assistant interaction, and we have probe script. How did we use the testbed and devices for doing the experiments? We have control experiments in which we automate the interaction with the devices using a companion app, or we use speakers for automatically asking questions to the device. For each device and functionality, we identify a trigger and a probe. The trigger is created for execute the functionality that can be switching on the light, for example, and the probe for determining if the functionality was executed. For example, for the smart bulb, the trigger is switching on the light through the companion app, and the probe is compare the screenshot of the app while I'm executing the trigger with the ground truth screenshot of switching on the light. We tested the probe 30 times against the ground truth and we got an accuracy of at least 80%, with the majority of the devices having an accuracy of 100%. We then need to identify the non-essential traffic, so we collect all the destinations and block them one by one. If the functionality succeeds when a destination is blocked, such destination is not required. Otherwise, we classify it as required. We set up the experiments testing as much as function as possible per device and category. For each of them, triggering and probing strategies was used, and probe success rate evaluation in 3 different points on time: May, July, and October 2020. So we take a sample screenshot of the app for each device for the desired state during a preliminary manually executed experiment, and then using the similarity to such screenshot to then infer the state of the devices. We also use traffic analysis for understanding when a television or a smart speaker devices activate, thus probing our function. We found that more than 50% of devices have non-essential traffic, mostly cameras, smart speakers and video, so devices that are streaming content. There are some possible explanations for this. First of all, complexity, so skills and apps in the case of these devices that are giving us content, or for example, uncommon vendors, so rebranding in the case of cameras. The number of non-required destinations is 62 against 57 destinations marked as required. Non-required destinations are contacted the most by cameras, speakers and video devices, but it also happens on simple devices such as the TP-Link smart plug and smart bulb, for example. Third parties are always not required, probably because of background app activity. In the case of the video streaming devices, Netflix. So some first support parties are also not required. Unfortunately, we cannot know why some first party are not required because the majority of the traffic is encrypted. The best guess is that those destinations are used for firmware upgrade or maintenance. The worst guess is that those destinations are used for data collection. There is a good news on all this. Non-essential traffic is relatively small, so less than 1 kilobyte per devices. However, it's still possible to transmit with these few kilobytes the presence of the devices, its status, basic data from the sensor, for example, open, close, door, some motion, some alarm. In this analysis, we check whether any destinations that are not required for a device are required for another devices. And we define this destination as device dependent. So knowing if there are any destinations that are device dependent is important since their existence means that a blocking approach to prevent non-essential traffic cannot rely only on a flat list of destinations. Rather, blocking of destinations must be device specific for at least some devices. So we found that 2 destinations are not required for some devices, but required for others, even for devices from the same manufacturer. We then investigate whether second level domains are enough for identifying non-required destinations. The figure shows the list of second level domains that are simultaneously required and non-required, and the list of devices contacting them as required and not required on the right. For 2.5 devices contacting the 11 second level domains in the figure, second level domains are not specific enough since both essential and non-essential traffic use the same second level domains. The main takeaway here is that while this simplification of using second-level domains is effective for identifying non-essential traffic for the majority of the devices we tested, it will lead to some mislabeling traffic for a significant fraction of devices. Our experiments demonstrate that devices from the same vendors tend to behave similarly, probably due to sharing some code among them and integrating them in the same IoT ecosystem. This enables the extension of a blocking approach based on our destination list to other or future devices from the same manufacturers. Our analysis does not show notable situations in which devices from different vendors contain the same non-required destinations, except for the case of devices in the video category, where both devices show Netflix video recommendation in their menu screen. As you know, there are already some ad blocking lists available, but existing approach like Pi-hole and others block destinations are mostly used for various web trackers, thus missing non-required destinations specifically for consumer IoT devices. So we compare our non-required destinations with Pi-hole, Firebug, Modero board, SOPAD list, and up to only 6 out of 62 non-required destinations are in existing block lists. So public block lists are of limited help in blocking IoT non-essential traffic. We determine whether the IP protocol and port are alone enough to detect the traffic to non-required destinations. The answer is generally no. We found that most non-required destinations constantly use HTTPS with just the following exceptions to domains using HTTP. Destinations do not change over time, so at least in our 6 months of experiments. To mitigate non-essential IoT traffic, we propose some blocking strategies. Blocking non-required destinations and allowing the rest of the traffic. This strategy only works under the assumption that non-required destinations are stable, so they do not change over time. And then we have the allowing leasing, so allowing required destinations and blocking the rest. The assumption of this strategy is still that required destinations do not change over time. We also verify this assumption on the same 3 sets of experiments over 6 months, noticing that required destinations also do not change. We believe that for the typical home IoT environment, a deny leasing strategy may be more appropriate, since maintaining the functionality is a high priority. And in this case, we propose IoTrimmer. That is an IoT blocking system composed of device acting as a router. This can be any computing devices such as a Raspberry Pi or a NAC, with at least 2 network interfaces. We have destination list, so the list of non-required destinations that we call IoTrim list, and we anticipate that the destination list will be maintained via options like crowdsourcing or by organizations that are willing to adopt our required and non-required destinations measurements methodology on a regular basis. Similar to what happens for lists to block trackers and basically advertisers from websites and mobile apps. To mitigate non-essential IoT traffic, we propose a blocking system composed of 2 components, IoTrigger and IoTrimmer. So the former runs our methodology to produce non-required destination list, and the latter uses such lists with a blocking strategy to generate firewall traffic blocking rules. There are some limitations regarding our blocking approach that we need to take on account. Risk of allowing non-essential traffic or to break device functionality. So destinations may change more frequently than lists that are updated. They can use the same destination for both types for eluding our blocking approach. We can have also some non-observable functionalities, like for example firmware update or time synchronizations, and also it's difficult to cover all the devices. So our methodology can have because we need to have input and output for every functionalities. But these limitations are not critical and also shared with other blocking systems. So blocking systems may miss or break something, but they are useful regardless. In this work, we have seen that the many contacted destinations are not required for the device to operate. The good news is that the quantity, so the number of bytes of data that we have sent to the non-required destinations, that are sent to the non-required destination, is very small compared to the rest of the traffic. However, even if the amount of data is small, it is still a concern from a privacy perspective, since it's still enough to signal the presence of the device and the function in use. So such non-required destinations potentially violate the data minimization by design principle of some privacy regulations such as GDPR. And unfortunately, many devices' privacy policies provide little information about how they use data from their customers' devices. In many cases, it is unclear whether the behavior of some devices is not consistent with what is stated. In conclusion, we propose an automated approach to measure non-essential IoT traffic. The main takeaway is that our housemates are stealthy, and existing block lists are not effective with IoT devices. We have designed and implemented IoT Trimmer, a system to mitigate IoT non-essential traffic using devices-dependent destination-based block lists. All our software and lists are open source and available for download. Thank you very much for your attention.